Hello, hello. Welcome to my talk on infrared absorption spectroscopy fundamentals. This will be part 1 of 2, and we're going to be talking about the fundamental basis of FTIR, Fourier transform infrared absorption spectroscopy. Before I go on, I want to just briefly go over my teaching philosophy a little bit. Whenever I learn a new instrument, I usually want to get answers to 3 main questions. Number 1, how can the instrument hurt me? Safety. You and I are the most important instrument. Number 2, how can I hurt the instrument? The instrument is often an expensive piece of equipment and you don't want to break it. And number 3, how can the instrument lie to me? That is, how can I get bad data? What sort of artifacts might occur? Those sorts of things. In order to know that, you need to know the fundamental basis of how the measurement works. Note that I'm not going to go over what buttons to push or how the software works for the most part. This is not a training video of how to actually operate the instrument. Knowing what sort of buttons to push will only teach you how to operate that particular instrument, and it doesn't teach you how to troubleshoot it. Whereas learning the fundamental basis of the measurement is something that you can carry over to any make or model of instrument. So with that, let's get started. So I'm going to talk about the fundamental basis of infrared absorption through the classical electrodynamic model because quantum mechanics is hard for me. I'm very, very sorry. Hopefully you have at least a high school or maybe first year undergraduate level of physics background because that's where we're going to start. We're going to start with a 2-mass end spring system as shown here. So suppose you have a mass MP and a mass MN. And the mass MP has a slight positive charge, and the mass MN has a equal and opposite negative charge. And the 2 masses are connected with a spring constant K. So 2 things about this system. Number 1 is that it will oscillate at a natural frequency given by the simple equation, square root of the spring constant over the reduced mass. The other thing about it is this is known as an electric dipole. It has 2 equal and opposite charges slightly separated from each other. So suppose this electric dipole, the masses can move, but the bond can't rotate. What happens to this system if you apply an electric field oriented vertically like so? What will happen is that the electric field will push the positive charge upwards and the negative charge downwards. So it will stretch this dipole. Similarly, if you switch the orientation of the electric field, then it will compress this dipole. So what happens if you apply an oscillating electric field? Well, the dipole will start to vibrate. And if you just so happen to apply an oscillating field at a frequency matching the natural frequency, then it will really start to oscillate. It will actually absorb that electric field energy very, very strongly. What is another name for an oscillation in the electromagnetic field? An oscillation in the electromagnetic field is a photon. It is light. In other words, if you hit this dipole with the right wavelength of light, you will get it to oscillate, and this dipole will absorb that light. It just so happens that if you have atoms for masses, suppose, for instance, that the positive charge is a carbon atom and the negative charge is an oxygen atom, and they're bonded by covalent bonds, the resonant frequency of this group is in the infrared range, around 4,000 to 400 wave number. So that is pretty much it. That is pretty much the fundamental basis of Fourier transform infrared absorption spectroscopy. The Fourier transform part of FTIR is not pertinent to this discussion. Fourier transforms are a very powerful mathematical tool. I encourage you to learn about them, but they're a story for another time. But this is really all you have to do. You take your sample, and to analyze it, you hit it with a range of infrared wavelengths, and you see what gets absorbed. You'll find a couple peaks, and each of those peaks will be characteristic of certain atomic groups, and you can figure out what your sample is made out of. So a couple little notes on notation here. Note that I'm reporting infrared frequencies in terms of this unit wave number. Wave number is just inverse wavelength. You just do a 1 over wavelength, and you'll get wave number. Pretty straightforward. The other thing is that a lot of the times when people plot absorption spectrum, they will plot it with wave number increasing to the left, not to the right, to the left. That's just one of those convention things that you'll see from time to time. But otherwise, that's pretty much it. if you just go back to this basic spring mass system, that actually gives you a lot of reasoning power to figure out why things will absorb at certain frequencies and how strongly they might absorb. So for instance, the carbonyl group, C double bond O, that has a characteristic absorption peak around 1700 wave number. But what happens if you were to replace that oxygen atom with a sulfur atom? Well, two things. One is that the sulfur is a heavier atom, and two is that the carbon-sulfur bond is a weaker bond. So both of those conspire to lower the natural frequency. So the first thing that happens is that the natural frequency of the thiocarbonyl bond is going to drop down to about 12 to 1000 wave number. The other thing to note is that if you don't have an electric dipole, then it's not going to absorb infrared light very strongly. The electronegativity of carbon and sulfur are pretty close to each other. Carbon and oxygen will create a strong electric dipole. Sulfur and oxygen will create a strong electric dipole. Both of those sorts of groups will absorb very strongly in infrared. However, carbon and sulfur will not create a very strong dipole, and so won't absorb as strongly. So it will not only be shifting the peak, you will get a weaker peak as well. So that is the basic model, but now we're going to start layering on a little bit of complexity. The first thing to note is that I only talked about motion of the atoms vertically, but really we're operating in three-dimensional space. You can also get vibrations that are side to side or in and out of the plane of the board. And second thing is that you usually aren't dealing with a system that is only two atoms. You're usually dealing with a system that has multiple atoms. And those multiple atoms are connected to each other. And because they're connected to each other, mechanical vibrations can get translated through the molecular structure to each other and cause what is known as mechanical coupling. And so you can get cooperative motion of these atoms. As an example of mechanical coupling, you can take a look at the ethyl group, CH2 group, a very common group in organic molecules. What will happen is that the motion of each of these hydrogen atoms will be coordinated with each other. They can be either in phase or out of phase with each other. And again, not only that, they're in three dimensions. They can move up, down, left, right, in, and out. So you'll get actually 6 different vibrations from this group. So the first two are the symmetric and antisymmetric stretching vibrations. You get one stretching vibration where both of the hydrogen atoms are in phase and one stretching vibration where both of these atoms are out of phase. So you'll get actually 2 peaks at 2 different vibrational frequencies. Or they can move side to side, and that will give you the scissor and rocking deformations. Now, most of the time, these first 3, the symmetric, antisymmetric, and the scissor deformation, are the strongest absorption peaks that you'll see for this particular group. But you can also get a couple others depending on the situation. The hydrogen atoms can move in and out of the plane of the board, and that will give you the wagging and twisting deformations. Now note that, again, we're dealing with electric dipoles, and a dipole is a vector. That means that it has both a direction and a magnitude. So in the first case of the symmetric stretching, both of those dipoles are moving upwards when they oscillate. If you just imagine each of those individual vectors as adding up, then you'll get a dipole moment that is oriented vertically like so. Similarly, with the antisymmetric stretch, you sum up the vectors and you'll get a horizontally oriented dipole moment. The scissor deformation is going to be vertical, and again, these first 3 are usually the strongest vibrations that you'll see in infrared. The wagging deformation, if you do, again, the vector addition, the dipole moment of that is going to be oriented into the plane of the board. And the twisting deformation is not FTIR active. If you actually add up the vectors, you'll note that you will get 0. And so this does not absorb strongly at all in FTIR unless it's coupled to other vibrations. So keep that in mind. Again, it's all about electric dipoles and oscillations of the electric dipole. If you don't have an electric dipole, it's not going to show up very strongly in FTIR. So we're going to go over a little bit about spectral interpretation. There is a lot about spectral interpretation. We're just going to cover general regions. It is going to be impossible for me to cover every possible thing. So we're going to start by looking at an example of some FTIR spectra, and I'm going to cover what you typically see going from high wave number down to low wave number, going from left to right. On the left-hand side, what you mostly see are hydrogen stretching vibrations. These two very sharp peaks, those are typically stretching vibrations of alkanes. So these are very characteristic, very sharp. Out here, you'll often see broad absorbances, like really broad humps, and those are usually attributed to hydroxyl or amine or amide stretching, OH or NH stretching. Way out here, this is gaseous water. This is not necessarily water associated with your sample. This is actually atmospheric water inside the instrument. Sometimes you'll see a forest of peaks here, and just note that that is due to the atmosphere. That is not necessarily due to your sample. So moving over to the right, you have this large flat area that we like to call no man's land, because there really should be nothing here, unless you have some special groups like maybe cyano groups will show up in here, but otherwise, most of the time, this area is completely flat. Diamond will show up if you're doing something called ATR, attenuated total reflectance, FTIR spectroscopy, if you encounter a particular artifact. Also, carbon dioxide, again, this is gaseous carbon dioxide, not part of your sample, but part of the atmosphere within the instrument. So far, it's been pretty easy. You have the hydrogen stretching region out here, and you have no man's land out here, and then over here is where everything else absorbs, and it is quite the mess. This is called the fingerprint region. Now, to be fair, it's actually not too difficult to identify most of the peaks up until about 1350. At the front end of the fingerprint region is usually the carbonyl peaks, the C double bond O groups. Those are things like carboxylic acids, ketones, aldehydes, so on. They usually give a very strong, very characteristic absorbance around 1700. Next to that, you'll get phenyl ring breathing modes, alkenes, a couple other things. Out here, around 1450 or so and high 1300s, you'll get the two deformation vibrations due to alkanes. Those are usually the strongest peaks that you'll see here. If your sample has nitrate groups in there, then those can also show up here, as well as sulfates. Past that, it really gets very convoluted. It takes a lot of reading and a lot of looking at spectra to positively identify the peaks and not confuse them with other peaks that are in the exact same position. For instance, this is a spectra of bitumen. The literature often attributes this peak right here to sulfoxides, and there's some good work demonstrating that this peak is sulfoxide, but there is a problem here. This peak is in the exact same location as you might find a silica peak. And silica is sand. Silica is dirt. Silica is rock. Silica is everywhere. Silicon and oxygen are two of the three most common elements in the Earth's crust. So if your sample is contaminated with dust or dirt from the outside, that is something that you have to be careful of, and that can really contribute to messing up with your spectral interpretation. A little bit past that, you will often see deformation vibrations due to alkanes or phenyl groups. That's the set of peaks right here. But the main takeaway is that compound identification requires matching a pattern of many peaks. Most of the time, you cannot point to one peak and say, oh, I definitely have this compound here. That is very rarely the case. Usually, a group will show up more than one peak. You have to make sure all of those peaks are present. The other thing that you should consider are absent peaks. It's equally important to know what peaks aren't there to tell you what compounds aren't there as well. So in terms of spectral anomalies, as I mentioned, carbon dioxide and water can show up in your spectra. These are gases in the atmosphere of the instrument. If the atmosphere inside the instrument changes between taking your background and taking the measurement, then you will see peaks from these two gases. Water is really the worst offender. You will get two sets of peaks, one out near 4000 wave number, This usually doesn't interfere too much with your spectra, but the second set of peaks really does. This one out around 1500. This hits the front end of the fingerprint region and can really mess up your spectra quite a bit. So you have to kind of be careful of that. Carbon dioxide usually isn't a problem. Usually it's just these two peaks that sit right in no man's land. There's another thing that can happen, as I mentioned, with ATR, and that is that diamond absorbance peaks can show up. And those also will show up a set in no man's land, but can also contribute to noise and spurious peaks right at the lowest end of your spectrum. So you have to watch out for that as well. So that is it for part one. In the second part, I'll go over more specifics about how the measurement is taken, what the instrument looks like, and what sort of artifacts are associated with that. So, thank you very much. If you have any questions, reach out to me, and I'll be happy to answer them. Thank you.